All right, so what we talked about on Friday, we said a rational function is a function of that point. With R of x, okay, we use R usually as a rational. You go P of x divided by Q of x. Where P of x and Q of x are both polynomials. Now, they could be, any type of polynomial. They could be a monomial. They could be one term. They could be an integer, okay? They could be quadratic, cubic, quartic, whatever. And they don't have to be the same degree. The top one could be cubic, the bottom one could be quartic. The top one could be cubic, and the bottom one could be quadratic. It does not matter, okay? It's just two polynomials, one on top, one on the bottom, and we're going to analyze them through division and kind of see what happens with their graph. Now, the most kind of simplistic, a lot of times what we call the parent function of the rational functions is 1 over x. Okay? So this is kind of the idea where, 1 can be considered a polynomial. It's kind of boring, but it is what it is. Okay? X can be considered a polynomial. It's boring. It's monomial, but boring. But we're comparing two functions through division to get this rational function. So let's kind of analyze this graph. Okay. The idea here is, if I choose just some key points, remember key points on parent function. You know some key points on x squared. You know key points on cube root of x, square root of x, absolute value of x. All those functions, you took a handful of 3, 4, 5 points and hopefully committed those to memory. We'll do the same thing here. I should have 1 over 1, right? Okay, so 1 comma 1. If x is 2, I have 1 half. If x is 1 half, I have 2. Those 3 points, now maybe you don't see it so much with the first one, 1 comma 1. But if I look at 2 comma 1 half and 1 half comma 2, those ordered pairs are somewhat reciprocal to one another, right? Sometimes this is referred to the 1 over x is sometimes referred to as a reciprocal function. Okay. Now I'm also going to have the same thing, but they're going to be negative. Okay. So I should have. I don't know if I can do this. I'm going to negate A. Yeah. Negate B and negate C. That gives me those points there. Okay. Those are the 6 points that I would commit to memory to graph 1 over x. All right. Now, when I graph 1 over x, there's a couple things that are important for us to understand. Okay, let's take this point G. Make it blue, and just let me hide these things. Let's just look at that point G. Okay. As I move G, I'm going to move it to the right. Okay, so the x values are getting larger and larger. What is happening to those y values? They're getting what? Getting smaller and smaller, right? Okay. Now I'm out to, I think I've got it set to 10 decimal places here. Right now I'm out to 25 on the x-axis. If I keep going, eventually you can kind of interpret that eventually, because that's going to go to a 0 eventually, that will become a 0, that will become a 0. Eventually this 4 is going to become to 0, right? The idea is that we've actually got a lot more decimal places than just, I think it was, what, that 4 there, okay? So these would become zeros. And then if I had the ability, I could show you 5 more decimal places, and those would become zeros, and I can keep doing that, okay? Ultimately, that y value there is non-terminating, non-repeating. Does that make sense? Okay? And I'm going to be able to realize that as x gets bigger and bigger, that value gets smaller and smaller. Will it ever get to 0, though? No. It'll get close to it, but it'll never get to 0. Because think about it algebraically, 1 over x. Okay? The only way that I can get 1 over x to spit back a 0 is if somehow I could change my numerator to be 0, right? Does that make sense for some x value? There's no variable component to my numerator. So my numerator is always 1. So it can't become 0. Because 0 divided by 12 is 0, 0, right? Okay? So somehow maybe if I have an x value of 12, can I get my numerator to become 0? That's impossible here because there's no variable component up there. Okay? So we cannot do that. So there's no way that thing can turn to 0. Well, we can get really, really close because 1 divided by a huge number, 1 divided by a million, 1 divided by a billion, 1 divided by a trillion, that number is getting closer and closer to 0, right? But divide by a million, divide by a billion, divide by a trillion, divide by a quadrillion. Every time I do that, all that happens is that 1 in my decimal spot just keeps getting moved to the right further and further, right? It never gets to 0. That 1 can have as many zeros as we want in front of it. It will never turn into 0. So what do we call that? Okay. When we talk about a situation when x is getting really, really, really big, and my y value is getting really, really close to some number, okay? And in this case, that number is 0. It'd be that red line there, okay? We consider that red line a horizontal asymptote, okay? Because it's showing me what is happening to my y values as x gets really, 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 really big, okay? Now, if we think about how that compares to polynomials, and polynomials, we talk about polynomials, and we say, what happens to the y value when x gets really, 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 really big? We were talking about in behavior, right? Okay? That's ultimately what a horizontal asymptote shows us. It shows us the in behavior of our function, what it's doing in the long run. Does that make sense? Okay? Now, I think that's a bad word, asymptote, for that situation. Because when I look at this function, what are you not allowed to divide by in that function? 0, okay? So you cannot use the number 0. It's not part of our domain because it gives you an undetermined or undefined value back. So what we do, we realize that we put in a visual reminder at x equals 0. Okay, we put in that visual reminder x equals 0 that you cannot take that number off the x-axis and plug in your function. Because if you do, you don't get a y value back that you're able to graph with that x value. Does that make sense? Okay, so there should be no point on that curve. So here's the idea. If I go back to, I don't know if I can pull G back. Okay. Get G back in here, and actually let's do it this way. Let's not deal with G anymore. That'll take too long. Use H. All right, so as I take H, now, just because of the way the computer works, eventually it's going to flip over to the other side of the curve. But as I move H and it's getting, there it flips. I don't know if I can change. Let me do it this way. As I take H, and slide it, okay? You can see your x values are getting closer and closer to what number? 0, okay? Now, I'd have to keep doing, just to make sure it doesn't flip over the x-axis, I gotta kind of keep doing this little game of zooming in, zooming out. It's kind of a pain in the butt. But that thing will get closer and closer to 0. Will I ever get to 0? No, because that's what the asymptote tells us, right? If I zoom out, let's see here, let's go to I ain't doing well with it. All right, so I go up here to a very, very large y value. Now, whether you think 1,500, 2,000, if those are very, very large numbers, that's, I guess, your opinion relatively compared to like a billion. Those aren't very big. But the idea is at a y value of 3,000, I should still be able to zoom in. You see, when I click there, that is the curve 1 over x. Click there, that is my asymptote. Is there still a gap between them? Yeah. I go off at 300 million on the y-axis. I go off to, 3 Googleplexes on the y values and zoom in far enough and see if there's a gap between the asymptote and the curve. Okay, so that is a vertical asymptote. Now, that's how we want to think about asymptotes, that we do not cross them. Okay, that's why I think calling that red line a horizontal asymptote, even though that's what the math community does, is kind of a misnomer because of how we associate a vertical asymptote in the behavior on a vertical asymptote. If I can't cross a vertical asymptote, most people are going to think you can't cross horizontal asymptotes, but you can, and it happens pretty frequently that you cross horizontal asymptotes. A horizontal asymptote is only telling us the end behavior. Okay, it doesn't really tell us a whole lot about what's going on relatively close to 0, 0. Okay, and we'll talk about the algebra that we use to determine whether we cross it. And actually, I'll just give you a real quick one here. So we've determined our horizontal asymptote is y equals 0, right? Does that make sense? Okay. Well, if this is ultimately a function y equals 1 over x, right? If I want to know if those two things intersect or if they cross, don't I set them equal to each other? I think 1 over x is equal to 0. And then I just go through and try to solve. Well, if I'm trying to solve this, the first thing I do is multiply both sides by x. Figure 1 equals 0. What kind of statement is that 1 equals 0? It's a false statement. Okay? And the fallacy of that, guys, tells you then you do not cross the asymptotes. Okay? If you were to get an answer like x equals 3, that tells you cross your horizontal asymptote at an x value of 3. Okay? And we'll talk about then, and we'll see if that happens and how what y value that is and all that kind of thing. Okay? But you can, if you get false statements when you set your asymptote, your horizontal asymptote equal to your rational function, and you get a false statement back, you do not cross it. Okay? If you get a solution back, something that makes sense back, then that's where you cross it. Okay? You'll never get ultimately what we call a, we call that a false statement. If I would got like 1 equals 1, that'd be a true statement, right? When I algebraically get a statement like 1 equals 1 or 2 equals 2, something like that, it essentially tells me the two curves are the same curve, and that's not going to happen. Your rational asymptote, so your rational function is not going to be the same function as your asymptote. Okay. All right. So we have a little bit of understanding now of 1 over x. You guys agree with that? That's kind of that parent function. Okay. I want to talk about taking that thing and talking about its domain and its range. Okay. What is the domain? The domain of this function. What are the x values you're allowed to use? Everything but 0, right? So we write that negative infinity up to 0, union 0 to infinity, right? It's been a while since we've done that because we haven't really talked about any new functions lately. Okay, but that's how we deal with it. Okay, if you remember back to the beginning of working with polynomials, we started doing that with polynomials, but then all that work we've done chapter 3 so far. The domain for any polynomial is all real numbers, right? Okay, that's why maybe we haven't talked about this in a while. Another way of writing that, you might see if you were to read a PowerPoint, it's going to say x such that x cannot be 0. Okay, I like to write it this way: x such that x is an element of the real numbers, but x cannot be 0. When I'm telling you just this, when I write it this way, x cannot be 0, and there's no other components of that, basically I'm telling you then x is allowed to be anything that I didn't write down, right? This is just giving my restriction, so that's allowed to be everything else. I think this is more informative, but either one of those is fine. Okay. The range then, guys. Okay. What y value will you never have? 0. So my range is also negative infinity to 0, union 0 to infinity. Now, if I want to write that, we'll call this set builder notation. So if I want to write that blue statement in set builder notation, I could write it this way: y such that y is not 0. or y such that y is an element of your real numbers, or y is a real number, except for cannot be 0. So those are some options of how we would write the domain and range. Now, predominantly speaking, WebAssign is going to do the interval notation because it's easier for it to grade. But as you read text, as you read example problems that I might give you, worksheets, whatever, they might flip back and forth between those two notations. All right, so here's my question. What is the graph g of x equals 2 over x minus 3 going to look like? G of x equals 2 over x minus 3. And I want to go through this, and I want to use transformation ideas, okay? So if you guys remember something like this, if I would have given you previously in chapter 3, is like section 3.1 or something like that, I gave you something like y equals, let's do an easy one here, 4x plus 4. And I asked you, okay, take, you know it's x squared, you know it's a parabola, right? But can you graph that using transformation? Can you rewrite that so that it looks like this? That's really what that would be, right? Now, I probably won't write plus 0 on there, but we would transform it so it looks something like that, right? Because our goal is to try to get this thing so that x squared is being used as kind of your parent function. And then you've got that adding 2 before I square it, so it should tell you to move it left 2 units, right? Okay. So we've got that idea, and then we see that, well, okay, then move left 2 units, there's no vertical shift, there's no stretch or anything like that. That's how I would maybe use transformation to do that. So there should be a similar approach when I see a rational function like that blue one, g of x. And ultimately, guys, the first thing you're going to do is see if you can divide out the numerator. Divide out, especially when it's an integer here, just pull that thing out. Okay, so divide everything out by 2, and what that's going to end up looking like is 2 times the quantity 1 over x minus 3. So this is 2 times that. Does that make sense? If you multiply that 2 back through, that's exactly what you would get is 2 over x minus 3. Now, why would we do that? Because now I can see the 1 over x. Does that make sense? Instead of a 2 over x, I see a 1 over x. What's that 2 tell me I do to every single one of my y values? Is that a vertical stretch? Make sense? When I subtract from the x, going back to something like this, if I had x minus 2 squared, what's that minus 2 going to do to my parabola? Move it to the right 2, right? So what's this minus 3 going to do to my 1 over x curve that I have up there? Move it to the right. Okay, and that's going to happen to every one of those key points, A, B, C, D, E, and F. Okay, so if I take my point, I'm just going to do it with 1, 1 real quick. Okay, so if I take 1, 1, all right, so I'm going to stretch it by 2, so it becomes 1, 2, right? Does that make sense? So 1, so that's a stretch of 2. But now I got to move it to the right 3. So moving to the right 3 is going to take that value and make it what? 4, right? Okay. I'm going to take this point 2.5. 2 comma 0.5. And I'm going to amplify it by 2. So what's going to happen to my y value? It's going to become what? I multiply that by 2. It becomes 1. And now the right movement of 3 is going to make that number become 5, right? Okay. Now I'm not going to do it. So that's kind of what we'd be doing with all these points here. If I were to graph 2 times 1 over x minus 3, you get that red curve. Does that make sense to everybody? Okay. Now, Let's talk about what also happens here. I'm going to hide the black one. That's the parent function. What happens to this line here? Where does it go? To 3. Because algebraically, isn't that where we would divide by 0? All right, so when you guys are kind of transforming these rational functions, we know the parent function 1 over x has a vertical asymptote at x equals 0. When you start shifting your entire curve left and right, the asymptote goes with it. Okay? Does the vertical asymptote move here on? No. Okay. Think about why. You know, if x gets really, really, really big, okay, 1 divided by 1,000,000 minus 3 is still pretty close to 0, isn't it? Double is still really close to 0. So that thing's going to get to 0 as a horizontal asymptote again. The only time that horizontal asymptote would move is if I had what kind of shift? A vertical shift, right? Okay. But this is now the graph of that function, which is a lot easier to graph this way than it is in that format. Okay. Let's talk about the domain of this thing. What x value are you not allowed to use? 3. So my domain is negative infinity to 3, union 3 to infinity. What's your range? The only y value is that would not show up. 0. And again here, you know, so to see if I actually cross the horizontal asymptote, I would take 2 over x minus 3, see if it's equal to 0. When I cross multiply by x minus 3, so I get 2 equals 0. That's a false statement, so no, I don't cross it. Okay. Is that right, everybody? Transformation of 1 over x. Now it gets harder because of how these functions kind of end up looking or starting at. Let me give you, I can't remember what it was in the PowerPoint. Three x plus 5 over x plus 2, 3x plus 5 over x plus 2. Okay, so this one's a little bit different than the last one in regards that now the numerator is not just an integer term, right? Okay, it's a linear polynomial up there on the top and a linear polynomial at the bottom. And in order to transform this, what we actually have to do, guys, is rewrite it using long division. Okay, I can rewrite this using long division. Let's see what 3x plus 5 divided by x plus 2 actually looks like. 3x plus 5 divided by x plus 2. Okay, and this could have been something that you also did on the last one as well, but dividing the 2 out is just a little bit quicker. We need to go right here so that I do this long division correctly. I need to go right there. Say again. Remember, I'm trying to find, because it's kind of working backwards in what division is, right? So we want something that when I multiply by x, it gives me 3x, don't I? Okay. So you guys, we're not retaining as much information as we should be through previous stuff. Okay. So when we do this long division, we're looking for what number I put there. So when I multiply by this, I get that. So I get 3 times x gives me 3x. 3 times 2 gives me positive 6. Now I change the sign and I add straight down. It gives me negative 1 there. Now I stop because that negative 1 is of a degree that is less than x plus 2's degree. Okay? So what is that negative 1 called when I do long division? A remainder. Okay? So if I had, if I asked what 16 divided by 5 was, you would tell me be 3, 15, be a remainder of 1. So you say 3 and 1/5, right? 3 plus 1/5 is the exact same thing as 16 divided by 5, correct? Okay? So doesn't it make sense then that 3 minus 1 over x plus 2? The remainder over the divisor. That's what I did here. Remainder over the divisor, right? Add that to my quotient. Shouldn't that be the same thing as 3x plus 5 over x plus 2? Okay. Now, why is that a better way of writing it if I'm going to use transformation? Do you see the 1 over x now pop out? Okay. So let me clean this up a little bit. Three x plus 5 over x plus 2. We just figured out that is the same thing as 3 minus 1 over x plus 2. Now, I don't like it written that way because I like to see the parent function come first. Okay? So I'm going to use my commutative property and do this. Is that fair to say? What's that plus 2 going to do? Left 2. There we go. So that moves it left 2. What's that negative going to do? Reflect over x-axis. What's that plus 3 going to do? Vertical shift up 3, right? Okay. Now, if you remember, there was issue with the order we do transformations when we have reflections and vertical shifts and horizontal shifts as well. So we kind of adopted that phrase that we're going to use. We're going to do horizontal shifts first. We'll do stretches second. We'll do reflections third, and then follow it by vertical shifts. If we do that, we should get the right information every time. Okay. So I'm going to take just a couple of these points. We tried. I want to go 1 over x. So that's the parent function that we're going to do these shifts to, or these transformations to, and it should then produce that function. Now I don't think I can pull. I can't grab the whole thing and move the whole thing. All right. So let's just do this with the point 1, 1. Okay. So if I start with the point 1, 1. Okay. It says do horizontal shifts first. Okay. So what's the plus 2 going to do to that point? Let me just give me a second, real quick. Let's see if I can do this. Plot those like that will give me. No. Try list 2, 3. Awesome. Good job, sir. All right, so if I make a list of points 1, 1, 2, 0.5, 0.5, comma 2, and negative 1, negative 1. Let's just do one more. Negative 2, negative 0.5. All right, so I just want to go through and I want to do the transformation to each one of these points. So basically, the left 2. What am I going to do to each one of these x values? Subtract 2 from them, right? Okay. So what's that one going to become? Minus 1. What's this one going to become? 0. What's this one going to become? Negative 1.5. What's this one become? Negative 3. And this one's going to be negative 5, right? Okay, so we've moved them all to the left, too. That was the horizontal shift. Are there any vertical stretches? Negative 4? I was thinking 3. All right, so we moved them all to the left 2 units, right? Okay. There's no vertical stretch or horizontal stretch, okay, because there's no multiplier out front here, right? Like the last one had 2 out front, this one doesn't. There's a reflection. It's a reflection over the x-axis. So what is that going to change? So y values, it's going to make them all the opposite sign. So everything that's positive becomes negative. Everything that's negative becomes positive, right? Okay, so we've done that. Now what's this vertical shift up 3 going to do? Add 3 to all. So that one's going to be 2. This one will be 2.5. Okay, so now I'm going to graph those all at once. So it gives you those points there. Okay. And now I'm going to see if 3x plus 5 divided by x plus 2 goes through those points. Does that kind of make sense to everybody? So you can use your parent function points and use transformations to kind of develop that blue curve. Now, when I do that, when I develop that blue curve, it's kind of, I think, more work to go that route. So I had to do that long division, right? Now, that long division shouldn't be out of anybody's abilities, but it's maybe more work than what's necessary as we start to kind of work through some of this rational function work through the next couple of days. But when I look at this, what I want you guys to understand, if I did, what was it, 3 minus and 1 over x plus 2, it's the exact same graph, right? In either format, it's the same thing. Let's talk about the domain and range of these things, okay? What is the domain? So we're talking about these two functions here. The domain, back to this one, x cannot be what? 0. The domain here says the x cannot be, yeah, so it's x such that x cannot be -2, or write it in set notation. All right, so now my range, okay, and maybe we ask this question: Can I cross? Thinking about what happens here is my vertical asymptote, my horizontal asymptote is actually that number right there. Okay. My question is, does my original function cross it? So what we would do is we take 3x plus 5 over x plus 2 and set that equal to 3. Does my original function cross the asymptote of y equals 3? Cross multiply, you get 3x plus 5 equals 3x plus 6. And what do you get when you start working through this? You get 5 is equal to 6. What kind of statement is that? False. Okay. So do I cross that asymptote? No. Okay. But I do have an asymptote at 3. So my y values are y such that y cannot be 3. You see in this case, if I were to graph them, and I don't have my keyboard up here, I'm not going to, but you can kind of visualize that there would be a vertical asymptote there, correct? And a horizontal asymptote there. And the reason for doing this problem is to show you that you can, that you do move your asymptotes with your transformation. Okay, they are part of our graph, even though they are not points that we plot on our graph. Does that make sense? Okay, so the orange curve is our graph, that's our function, but we need those dotted lines as components to get it done correctly. Okay, that's the idea of asymptotes. You do not cross vertical ones. You could potentially cross horizontal ones. This transformation process, guys, I've never done it with anything other than these linear functions, and then the top and the bottom, the numerator and denominator. I'm going to venture to say that you could do similar things with 1 over x squared, okay, and then say, okay, well, what happens if my polynomials are both x squared? One on top, one on the bottom, both x squared. So we could probably do that. But what would I have to understand is that what x squared, 1 over x squared parent graph looks like. And it's not out of the realm that we might talk about this course yet. We might eventually start talking about 1 over x squared because it is a common function that we see elsewhere. But that's 1 over x squared. Okay? Because what happens when I square a number? It always becomes what? Positive. So when I square a negative, it's going to take the y value and make it positive, right? Now if I go x to the third, let's kind of look at what that would look like. Kind of like 1 over x, right? But you see how it gets kind of taller and faster, and it gets sucked down to that asymptote quicker? It's because of that power of 3, making those values, making those denominators so much bigger, so much faster. Okay? But what's x to the fourth going to look like? Yeah, it's going to look like 1 over x squared, right? Okay? But the behavior of going to infinity or going to 0 happens at a much more rapid pace because of how big that denominator gets relatively quickly. All right, so that division process here for these things and graphing these, it's feasible. It's not bad. It makes sense. It follows along the lines of everything we've already talked about. But there's a little bit of an easier method. So I'm kind of, and I don't want to say it's easier, and whether we get to these 8 steps or not today, on my website under 3.6, these are the 8 steps that we're going to use next week. Now, it's going to take because we got 6 days of no information from me in regards to a gap of time that's going to pass before we come back and talk about this, right? I'm going to pick up right where we left off. I'm not going to revisit everything we talked about today, okay? So you guys need to be able to retain that. We're going to talk about these 8 steps, and these are the 8 steps that we would use instead of the transformation process, okay? It is much quicker. A lot of times, some of those steps are already done for us in regards to the analytical algebra aspect of things, and it's just a little bit more convenient. But everything we talk about transformation should match up to it, okay? And talk about how to do the algebra for our asymptotes, okay? You guys remember when we did end behavior? End behavior. So by definition, I don't know if you got the definition up here. Somewhere. There we go. The definition of an asymptote here says, and this is a vertical asymptote, it says f of x, so x equals a is a vertical asymptote, okay? So x equals a is a vertical asymptote if the function f of x as y approaches positive negative infinity as x approaches a from the right or left. So what it means is this here is an asymptote as long as my graph starts to approach infinity from either side of it. Does that make sense? Okay. Now, how does that differ from what we've talked about already with this polynomial? Okay. This is still going to infinity, isn't it? But is it approaching a specific x value like a was? Like a is like 2 or 3 or 4, right? The specific x value. That x value is approaching what when I move this direction? Infinity, not a specific a value, right? Okay. So that's kind of the difference in regards to talking about the behavior of going as my y value goes to infinity. How do I know if that's because of an asymptote or because that's the end behavior of a polynomial? It's because of what x value you're approaching allows you to make that distinction, whether it's an asymptote or the end behavior of a polynomial. Down here, talks about the line y you see is a horizontal asymptote if your y values are approaching b as x approaches infinity. So if you read that, that's end behavior. That is exactly how we define end behavior. Okay. So you're going to see things like this, where you start to kind of move from the bottom left and come up here, and then you start hugging that value of b. You can see also the same thing here. And now there's also times, I was going to say a lot of times, your graph is going to kind of come back up and do something like that, where it starts to hug b from the below it. Does that make sense? Okay. Not always. You could sometimes have graphs that maybe there's a vertical asymptote here, and that thing starts to hug that vertical. Obviously, I can't cross it and go back up, right? But you'll see different behaviors around horizontal asymptotes that you would not necessarily see with a vertical asymptote. Okay. And let's talk about where, just kind of real quick, where the horizontal asymptote concept comes from. think about, remember in behavior of polynomials, right? In behavior of polynomials, if I had p of x is equal to 4x cubed plus 6x squared plus maybe 10. What term up there dictated my end behavior? 4x cubed, right? Remember doing this? Take the 4x cubed out, that leaves you 1 there. It would leave you 3 over 2x. And here it would leave you 5 over 2x cubed, right? And the idea is what happens when x gets really, really big, that goes to 0, the 3 over 2x goes to 0, and that goes to 0, right? And when x gets really, really big, the only thing that's coming into play is that right there, correct? So it told us that y got really, really big too, okay? Well, when I do p over q, p of x over q of x, now I've got two of these things. I've got maybe I'm going to write it this way, 4x cubed over 1 plus 0 plus 0 plus 0, however many zeros I need there. And now my denominator is going to be something of the same thing. Maybe it's 2x cubed, and then here I'd have 1 plus 0 plus 0 plus 0. Does that make sense? Well, what are these things? What are these 1 plus 0 is going to do? Cancel out. What are the x cubed over x cubed going to do? Cancel out, right? This is when x gets really, really, really big. So when x gets really, really, really big, the only thing I'm left with is 4 over 2, right? Which is just what? 2. Okay? So what we're saying here then is that when x gets really, really big, my end behavior is 2, so my horizontal asymptote is 2. But if I go back to the original polynomials that these came from, that 2 can be found through just dividing the leading coefficients. Does that make sense? Okay? We'll spend a little bit more time on Monday. We'll pick up with this, maybe do a specific example where I give you an expanded p over q, or sorry, p of x, and an expanded q of x, and we go through and we pull out the leading terms and see that cancellation, all that kind of stuff, and see how that then dictates our end behavior. But it's all because of how end behavior was dictated with polynomials, and here all we're doing is dividing two polynomials. Okay? That is when both the numerator and denominator have the same exponent. Okay, same leading degree. That changes when they're different. Have a great rest of the day.